Suppose I have an infinite sequence of random variables that are taken from the uniform 0, 1 distribution. And I'll define S as the random variable given by the infinite sum of each of these variables divided by 2 to the I. If I wanted to find the expected value of this sum, it would be simple, because I can write S as the sum, and then I can use linearity of expectation to write the expected value of a sum as the sum of expected values. Since 2 to the I is independent of x, I can factor out 2 to the I. It's just a constant. And the expected value of a uniform 0, 1 random variable is just 1/2. So I get this sum, and by using the infinite sum formula, the answer is 1/2. I want to make this problem a little trickier by not adding up all the terms in the sequence, but only some of them. I want to add up the first k terms in the sequence. I want to define S in that way. And k is going to be the number of terms in the initial descending sequence. So for example, if my infinite sequence begins with 0.7, 0.5, 0.3, and then let's say the next number is a bit higher. The initial descending sequence is just these 3, and I would want k to equal 3 in this case. The way we can define k is to say that k is the least positive number, I'll say positive integer, such that x sub k is less than x sub k plus 1, meaning this next term x sub k plus 1 is bigger, and that ends the initial descending sequence. So if I define S in this way, can we still find the expected value of S? That is the question. I'm going to carry over some information from the previous slide. This is our new definition for S, where it's a finite sum, and the number of terms in the sequence is actually a random variable called k. Now, informally speaking, I'd like to actually still think of this as an infinite sum. This is an infinite sum of x sub i's contribution, where x sub I could contribute x sub I over 2 to the I, but could instead contribute 0 if x sub I is not part of the initial descending sequence. I'd still like to find the expected value of S, and in order to do that, I'm going to have to learn something about when x sub I contributes 0 and when x sub I contributes some non-zero quantity. For simplicity, I'm going to suppose x sub I is equal to some fixed value t. And let's think about when does x sub I contribute a non-zero amount to the sum. What needs to happen is that x sub I up to x sub 1 up to x sub I minus 1 needs to all be bigger than t. So they all need to be elements of this interval from t to 1. And furthermore, x sub 1 up to x sub I minus 1 needs to be a decreasing sequence. So these are two things that I need. And it is precisely when I have these two things that x sub I will contribute a non-zero amount. To calculate the probability that each of these things happen, I'll start with the first one, Notice that this interval from t to 1 has a length of 1 minus t. So the probability that, let's say, x sub 1 is in that interval is just 1 minus t. And the probability that x sub 2 is in that interval is 1 minus t, and so on. So I have I minus 1 of these terms which need to be in that interval, and so this is the probability that that happens. I'm, for a moment, ignoring the fact that I actually want these terms to be decreasing, right? So I'm focusing only on this. For the second part, if I want x sub 1 up to x sub I minus 1 to be decreasing, the probability that that occurs is just 1 over I minus 1 factorial. Because there are I minus 1 factorial permutations of this sequence, and only one of those permutations will be decreasing. By exchangeability, each permutation is equally likely. So I can say that the probability is exactly this. Putting these facts together, I can say that x sub I equals t contributes to S with probability (1 minus t to the I minus 1 over I minus 1 factorial. I'm going to scroll up to give us more space, but I'm going to save this fact right here. This is important. I'm going to write the expected value of S using the infinite sum that I wrote earlier, the informal infinite sum, where each term is just x sub i's contribution. And by linearity of expectation, I can write the expected value of a sum as the sum of expected values. And in order to find the expected value of x sub i's contribution, I need to know the probability that x sub I contributes a non-zero amount to S, and we've calculated that. So I can now use the law of total expectation. This is going to be equal to, by the law of total expectation, the sum from 1 to infinity of the following integral. When x sub I equals t, and let's say it contributes, what it will contribute is precisely t over 2 to the I. That's due to the initial sum we had at the beginning. Remember, we're not adding up just x sub i's, it's x sub I over 2 to the I. Now, when it contributes this amount, it only happens some of the time. By the law of total expectation, we're going to multiply this by the probability that x sub I contributes that amount. And it's this quantity here. T ranges from 0 to 1. Those are the possible values for x sub I. And so this is our answer. We just have to solve it. So I'm going to factor out from the integral all the factors that don't involve t. So that's going to be all the denominators. I'll just copy over the information from the previous slide. And in order to calculate this integral, there are tricks you can use, but the simplest way to do it, I think at least the least creative, most straightforward way to do it, is to just use integration by parts, or equivalently, tabular integration, which is what I use. So I'm going to pick t, this factor of t here, to iteratively differentiate, which will give me the sequence t, 1, 0, and then an infinite sequence of zeros. The other factor, 1 minus t to the I minus 1, I'm going to iteratively integrate, which by basic integral rules gives you the following. And the way that tabular integration works is that you come up with an alternating series of products where I take these two terms, multiply them, and I add, take the next two terms, multiply them, and subtract, and so on. And since all of these terms I'm circling are zeros, I have a finite sum. I just have two terms in my sum. So I will write those out. This integral comes out to be t times this quantity minus 1 times this quantity. All of it evaluated from t equals 0 to t equals 1. When you substitute 1 for t, it's easy to see that everything cancels. 1 minus 1 is 0, so the first term is 0. And in the second term, I have 1 minus 1 again after substituting, and so the second term equals 0 as well. And so my integral is going to be 0 minus whatever I get when I substitute 0 in for t. The first term cancels, and the second term gives me simply negative 1 over I times 1 over I plus 1. So the expected value of s is the infinite sum of 1 over 2 to the I times I minus 1 factorial times the integral which we just found was this quantity. I can simplify this. This is just going to be I plus 1 in the denominator, factorial. And from here, it helps to know something about power series. Here's the power series for e to the x. Notice how it has this I factorial in the denominator, and our sum has something similar. If I simply rename I, it would also have an I factorial in the denominator. I'm going to go ahead and make this renaming. I'm going to multiply and divide by 2 simultaneously, just so that I get I plus 1 written both times in the denominator, so that when I make this renaming of I plus 1 to I, and I, of course, have to change what my bounds are, so we're going to go from 2 to infinity now, I've achieved this I factorial. As for the 2 to the I in the denominator, I can simply select x to be some appropriate value so that I get 2 to the I in the denominator. And that value is simple to come up with. Simply evaluate e to the 1/2 to get this. And by simple rules of exponents, here's the sum. We have 2 to the I factorial. So the only difference between e to the 1/2 and the sum that we're interested in is just the first couple terms in the power series. This sum is e to the 1/2 minus whatever the first 2 terms are in this power series, since we're not going to include I equals 0 or I equals 1. When I equals 0, the summand is just 1, and when I equals 1, we get a half. When we distribute finally, we get this, and that's the expected value of S.